I'm going to work without the PowerPoint today because we're reviewing for the first part of it. We're going to get back into naming compounds on page 66. Review for the first part and new for the second part. First part, we're going to talk about naming compounds, specifically naming ionic compounds. Mentioned 2 days ago on our last class time together that there are two different naming paradigms. There's one naming paradigm that's used, and don't let the word paradigm mess you up, okay? It's just two different ways of doing it, two different structures or patterns that they use. One pattern for ionic compounds and another pattern for covalent compounds. You shouldn't be intimidated by the phrases ionic and covalent for the compounds right now. Let's start with what a compound is. A compound is a structure of atoms or elements that have come together. Those atoms have formed a molecule. And so rather than it being something that's describing a single structure of an element, we're talking about something that has two different elements brought together to form a structure, a compound. Different colors representing different elements. They form a structure, form a compound, and the structure is known as a molecule. For an ionic compound, that means that one of the elements that make up the compound is a metal. We know that it's a metal if we look at the periodic table because it rests or resides left of the jagged line, realizing that hydrogen is an exception. Hydrogen should be a nonmetal, but it's depicted on this side, and there are other reasons why it's depicted here. The way it's depicted is not primarily on whether it's a metal or non-metal, it just works out that way. Okay, there are other reasons we'll learn later on why hydrogen is sitting right here. It's because it has a 1s1 electron. But don't worry about that for now. This is actually the exception. It's a nonmetal, but everything to this side of that jagged line we're going to treat as a metal. And if you look at a compound, if you look at that molecule, and there's at least one metal, I say at least one metal, you're not going to find multiple metals, except again, special cases, we're trying to keep it to some very basic things for this course. So look for a metal. If you find a metal in that compound, then it is an ionic compound. And if it's an ionic compound, its name follows the ionic compound naming paradigm. That paradigm means that the name of the molecule is going to start with the name of the metal. If you're looking at a compound and you see that it has a lithium, a sodium, a potassium, a rubidium, a magnesium, or calcium, or any of these metals, this side of that jagged line, if you find that within the symbols of the elements that make up the molecule, if you find any metals in there, it's an ionic compound. And if it's an ionic compound, its name is going to begin with the name of that metal. Sodium chloride starts with sodium because sodium is the metal. Potassium chloride starts with potassium because potassium is the metal. So if you find a metal within that structure, the name of that molecule begins with the name of the metal. Okay? Then after that, we're going to go to the nonmetal. And the nonmetal is going to have its ide name. It's not potassium chlorine, it's potassium chloride. And we recognize, you're going to find out later on why that name is. What's actually happening here is one element is giving up electrons to the other one. The other one is accepting them. The metal is giving away electrons, the nonmetal is accepting electrons. And in chemistry, that ide ending lets us know that this is going to be an ionic bond. Right now we're saying this is an ionic compound. We're going to find out later that the reason why it's stuck together the way it is because of the ions in it. Right now just know, hey, this is ionic because it has a metal. Its name begins with the metal name and ends with the nonmetal name, but the nonmetal gets its ide name. And that's from table 2.1 in your book. Because of the way the elements come together to form this bond, and I mentioned already that it has to do with giving and taking of electrons, the reason why we had just a simple metal, then nonmetal ide, if you look at that, you can't tell by the name how many of each there may be. Now, in ionic bonds, they only come together in one distinct pattern. Using simple examples of sodium chloride or potassium chloride, I know that for sodium chloride, when sodium and chlorine are together, the only way they combine is one sodium and one chlorine. On your ionic compounds, there's only one way those things can come together to form a molecule. There's only one that works. And so you don't need to be told how many within the name. You don't need to be told how many chlorines or how many sodiums or how many potassiums or how many rubidiums or how many fluorines, because you're going to learn very quickly that they can only come together in one way, and you can tell from this table what that way is real quickly. So for ionics, the naming paradigm is easy because it's going to be the metal and then the nonmetal with its "-ide name. Sodium and chlorine do not combine as N2Cl or Na2Cl, and they do not form NaCl2. It only forms NaCl because of the way they trade electrons. So that's the ionic compounds. The second naming paradigm is for the covalent compounds. Covalent compounds, to remind you, is a compound that's formed of only nonmetals. We're not going to have any compounds that have all metals. It's either going to have a metal and nonmetals, or it's going to be all nonmetals. Meaning that everything within that molecule, within that structure, is represented by something that is to the right of the jagged line. So you're not going to have a molecule that has more than one metal, but you are going to have molecules that have a metal and nonmetals, or all nonmetals. And those that are all nonmetals form covalent compounds. Covalent compounds are stuck together differently than ionic compounds. Again, this is a little bit of preview. Ionics come together because of their opposite charges, kind of like magnets. You bring them close together and they stick together. That's what happens in a metal-nonmetal combination. For an all nonmetal combination, a covalent compound, they are going to be sharing electrons. Nobody owns it, they kind of share it. That's all you need to know for right now. Matter of fact, that's not going to be part testable. What's testable for you is this molecule covalent or ionic? And if you look at every symbol within the structure, and every one of those symbols represents a nonmetal, then the compound is a covalent compound. Double checking to make sure we're recording here. So every element being a nonmetal means it's covalent. And when it's covalent, then we need to use the covalent naming paradigm. How do you name that thing? Covalents aren't as simple as ionics because ionics can only form in one way. Two elements come together, they only form one kind of a structure. For covalents, there's multiple different ways they can combine. Sodium and chlorine, example again, only forms a 1-to-1. It's the only way they combine. Covalent compounds that are made up of carbon and oxygen, we've already mentioned, have multiple ways they can come together. If I put a bunch of carbon and oxygen together, start again. If I put sodium and chlorine together, they are going to form a 1-to-1 bond, and they're going to form a whole bunch of sodium chloride molecules that look exactly like that. If I put carbon and oxygen together, I may have a carbon monoxide molecule. I could also have carbon dioxide molecules. Carbon and oxygen are the only building blocks that make up these molecules, and yet they come together in different structures. Here it's a 1 carbon, 1 oxygen, and this one here we're going to have a carbon and 2 oxygens. So covalents can form multiple different structures with the same building blocks. And so we have to have a way to name them that lets us know whether we're talking about 1 carbon and 1 oxygen coming together, or in this case, 1 carbon and 2 oxygens coming together. I need to have that within the name when I discuss it. And you have heard this term before for carbon monoxide, and down here, carbon dioxide. Within the name, carbon monoxide. And this would be carbon dioxide. See, I just can't say carbon oxide. If I use the ionic naming paradigm, it would just be carbon oxide. But there's not enough information there. Because carbon and oxygen to form a carbon oxide molecule could be a carbon with 1 oxygen, carbon monoxide, or carbon with 2 oxygens, carbon dioxide, which is why you need to memorize table 2.2. Table 2.2 is telling us whether it's a mono, a di, a tri, a tetra, and so on. So from the name, you can tell how many elements or how many atoms are coming together to form this one molecule. Well, in this one, 3 elements, 1 carbon and 2 oxygens. Carbon dioxide. When we write that one out, the CO2, think of it this way. This, what you would have put as a subscript, that subscript right there tells me that it's 2 oxygens, right? You take whatever the subscript name would be, and you bring it up in front of that element. So, let me give a little more space over here. CO2. The C is carbon dioxide. So you take whatever the subscript is, it's a 2. If you look at your table 2.2, the meaning of 2, the prefix is di. So when I see carbon dioxide, I know that I'm talking about 1 carbon and 2 oxygens, because it's carbon dioxide. Technically speaking, there should be or could be a 1 right there, but we don't write the 1 in chemistry because the 1 is assumed. Recognizing that, you might say, well, I've got 1 carbon, it could be monocarbon dioxide. That would tell me definitely 1 carbon, 2 oxygens. However, in the naming paradigm, we don't include the mono when it leads the name. If it's mono, we leave it off. So when it starts with carbon dioxide, I know that it's only 1 carbon because we leave off a leading mono. If there were other elements along the way that only had 1, their name would be in here, which is why, again, with carbon monoxide, CO, you might say that would be monocarbon monoxide, okay? Monocarbon monoxide, but by naming convention, we leave the leading mono off, and it comes simply carbon monoxide, carbon monoxide. Example 2.4 says to name the compound whose chemical formula is Al2O3. Al2O3. That's what we're trying to name, that molecule right there, that compound represented by this molecule. First of all, how many atoms are in this molecule? There are 2 aluminums and 3 oxygens for 5 atoms that form the 1 molecule of whatever this is. But we're going to name it right now. All right, looking at it, is this ionic or covalent? And how would I know? Okay, I've heard it's ionic, and it's ionic because aluminum is a metal. It has a metal and a non-metal, so it is ionic. So now I know in my mind I'm going to the ionic naming paradigm. How does the ionic naming paradigm begin? With the name of the metal. Start with the metal. The name of the metal is aluminum. Aluminum. Or if you're from Britain, it's aluminium. So that's aluminium. That's the way they would say it, aluminium or aluminum. So aluminum, we don't put the I in there, do we? Aluminum. I wonder why John Luc Picard said aluminium. So aluminum, do we need a di? There's 2, right? Do we need di-aluminum? No, because it's ionic. We don't use dis and tris and monos and tetras. It's just the metal followed by the non-metal name, aluminum oxygen, but we don't use the non-metal's name, we use its ide form of its name. So oxygen becomes oxide, aluminum oxide. You might say, I'm losing a lot of information here. It's telling me I need 2-dialuminum trioxide. Yeah, but you know what? You're going to very quickly be able to look at the table and know that the only way aluminum and oxygen come together is 2 aluminums combined with 3 oxygens, and that's the only way they come together, so we don't need all that information. It's superfluous. It's not necessary. Aluminum oxide is always Al2O3. There's no other way that aluminum and oxygen are going to combine that we're going to deal with in this class. So this is a metal and a nonmetal, which makes it an ionic compound. Ionics only combine in one way. So I use my metal name, my nonmetal name in its ide form, and this molecule is aluminum oxide. The second example, the second part of example 2.4 says, what is the name of the molecule whose formula is PH3? So ask yourself the question, ionic or covalent? I know if it's ionic or covalent because I'm searching for a metal. Do I find a metal in this? It's all nonmetals. Okay, all nonmetals, it's covalent. It's a covalent molecule. Because it's a covalent molecule, it has to follow the covalent naming paradigm. I'm going to start by writing out the names, because we don't have ide endings, or we do have ide endings, but we're going to start by saying I need to capture then my subscripts. What is the name of this first element? I'm a terrible speller. I'll just admit that up front. So, phosphorus, yep. Phosphorus. How many phosphoruses are there? One. You might think it needs to be mono, but we're going to remind ourselves in a moment that we don't need that mono, but monophosphorus. Prefix for the second element? There's 3 of them, right? Mm-hmm. My prefix is tri. And then the ide name of the hydrogen. So I look at that name and say, monophosphorus trihydride. If I have any monos that are leading, they're eliminated. So this goes away. If there was a mono in the middle someplace, it has to stay. And so the name of that molecule then is phosphorus trihydride. Because theoretically, there could be other combinations of phosphorus and hydrogen, other ways that they could combine, other than PH3. Theoretically. Aluminum oxide, there's only one way that we're going to look at that they can combine. So on your own, take a few minutes and try 210. Let's do let's just start 210. Let's try all 4 of them. It's really quick. It shouldn't take very long though. Yes, if you want to go ahead and just mentally figure it out, that's fine. I'd encourage you to write it down so that you're writing down what you believe it to be and find out whether you got it right or wrong. Because if you sit there and go, oh, I know it, and then we're up here talking and I say something that contradicts what you've written down, you go, oh, I could have figured that out. Well, you still would have missed it, right, on the examination. So take a moment, jot down the name of the molecule represented by CF4. So we'll name it Al2S3. P2O3 and CaO. Sulfur hexafluoride. You starting to talk like chemists already. Okay, so the molecule represented by the symbol CF4. Process, first, determine whether it's ionic or covalent. We determine whether it's ionic or covalent because we're looking to find a metal. If we find one, it's ionic. If we don't, it's covalent. CF4. So it's covalent. Al2S3. Oh, is it ionic or covalent?
Ionic.
P2O3. And CaO. Try again. Ionic. Calcium's a metal. So we found a metal in calcium. We found a metal in aluminum. And just so you know, if these molecules are written correctly, the metal is going to be in front. So if you're pressed for time, start at the very beginning, because that's where the name of the metal should be put if it's written correctly. Aluminum, salt, well, I won't give you the names right now, and calcium. See, calcium leads, aluminum leads. If the first one is a non-metal, unless they're intentionally jumbling them up to mess you up and writing them in an inappropriate or non-standard format. So start with the first one. Metal, metal, okay, these two are ionic. Then I'm going to go through and check these. Are there any other metals? No. Okay, they've written them in the right format, and I know it's like covalent or ionic. So for both of them now, I start by writing the names of the two elements. I start with C, which is a symbol for what? Carbon. Since it's covalent, do I need the prefixes? Technically, I do need the prefixes. I'm going to go ahead for now and write it here, knowing that in a moment I'm going to drop it. Monocarbon. Now I've got the second element. It's fluorine, but it has a subscript 4. What is a subscript 4? How do I write that? Tetra.
Go ahead, Mr. Baker.
Go ahead. Thank you. Okay, so we have monocarbon tetra for the number 4. The subscript 4 lets me know my next name is tetra. And then the I name of this element. Fluorine becomes fluoride. Look at that name, and I eliminate my leading mono if I have one, which I do. And so the name of this molecule is carbon tetrafluoride. Thank you, sir. Carbon tetrafluoride. Dropping the leading mono, it's simply carbon tetrafluoride. Why do I need to have the tetra in there? Because theoretically, carbon and fluorine can combine in different ways than just this. So I need to have that tetra captured. I need to know that. If I don't have tetra in there, I'm not sure exactly what I'm working with. Now the second one is ionic. Makes it simple because I don't need to remember, I don't have to use prefixes. I'm just going to take the element names. Start with the metal, aluminum. Second is sulfur, but because it's a ionic, I don't need to have trisulfide. I just write sulfide. The "ide" ending of sulfur. So this molecule is aluminum sulfide. If you said to me, if I asked you, what is the chemical formula for aluminum sulfide, you wouldn't be able to do that right now, but you would say, okay, well, but I know it's an ionic bond between aluminum and sulfur. It's got to be ionic. Why? Because there's no mono, di, tri in the name. It's just the element names. Third, P2O3, we said it's covalent. So we're going to start with the subscripts, right? In this case, we look at the first element. The subscript is 2. We communicate that by saying, what? Di. Di, the name of this first element, is phosphorus, right? Is it phosphorus? Yeah. Again, I'm going to just own my inability to spell. Diphosphorus. Subscript 3, tri, oxygen with its "ide" name. Look at my first, is it a mono? No, so it stays. It has to stay. This is diphosphorus trioxide. If I gave you, write the chemical formula for diphosphorus trioxide, you would write, okay, phosphorus with a subscript 2, oxygen with a subscript 3. There's my molecule. Diphosphorus trioxide. And the last one, calcium and oxygen, it's ionic. So this would just be the element name, starting with the metal. Calcium oxide. Not calcium monoxide, just calcium oxide. Why? It's ionic. No prefixes. Just the elements' names. Metal name, non-metal in its "ide" form. Now looking over to the right-hand side, we're going to work it backwards. The formula name, or the chemical compound name, is sulfur hexafluoride. Start from the front. What's the chemical symbol for sulfur? Just an S. Next, what is the chemical formula or symbol for fluoride? Well, "ide" is the ending of fluorine, right? And we look over there, and it's an F. Now we need to deal with the prefix, which was hexa. 6. That's sulfur hexafluoride. Pentacarbon decahydride. I don't know, it's too long. That's scary. No, it's simple. Look at look here. You see a prefix here. You see a prefix here. You see a chemical name or element name there, and you see an element name there. Start by writing the symbols for the elements. I have a carbon, and I have a hydrogen. And look at the prefixes. Penta. Meaning of penta is 5. 5 carbons. Deca. 10. That is pentacarbon decahydride. C5H10. And so everything we're going to talk about naming, yes sir?
So the phosphorus one, why didn't you take out the di? Is it because it's not mono?
It's not mono.
Okay.
The only thing you eliminate is a leading mono. If it's a leading di, tri, tetra, penta, hexa, it stays. You just eliminate it if it's a mono, because it's assumed. If it wasn't at least a mono, it wouldn't even be there at all. But if it's a di, I need to know that, because that changes how I understand the pieces come together. So you only eliminate leading monos. Any other prefix stays. So no compound should ever start with a mono whatever. Just the mono goes away. And every compound we deal with in this class is going to be either an ionic or a covalent. In this naming paradigm, there are other naming paradigms. There are other more complicated chemical compounds that you could run into in upper level AP chemistry or college chemistry, but not for this course. Everything is going to be either ionic or covalent, and it's going to follow one of those two naming paradigms. Okay, so that brings us over to page 69 now. and we are on classifying different types of matter. And if you were to flip ahead, you're going to see that we're really into about the last day's worth of instruction. A lot of graphs and all the lab in the middle there, which we may or may not do. I may do it for you or with you, but very little more content than we need to have. So that's why the plan is for Friday, review questions. Monday, practice problems. Tuesday, extra practice problems. Wednesday, this is the homework, and this is in class. That's what we're going to do in class. In class, we're going to do content on Friday in here. We're going to do the review questions, do the practice problems, extra practice problems. Thursday in class is a module test. So again, if you're not already memorizing table 2.1, 2.2, the bold on 2.3, get on that now. If you wait to hear to do it, it's going to be hard to catch up. You need to know you know it when you're working these problems. It'll help you if you get the problems right, that you know it. Thursday, because Friday is a school day, but it's also parent-teacher conferences, half day. And I want to have grades in from this for those parents that come in on this day. I want to have 2 grades in time. All right. Classifying matter. You'll notice under the section there's 2 blue definitions of a pure substance and a mixture. Let's just look at it and read them right now. A pure substance is a substance that contains only one element or compound. A pure substance. That means if I have a sample, and I may do this, if I have a sample, in other words, I've got a handful of stuff, and everything that I have in my hand is the same stuff. It could be all carbon, could be all potassium, it could be all of any one element, meaning that I've got a whole bunch of atoms in my hand. Or it could be that everything that I have in my hand is a compound, but it's the same compound. It's all, sodium chloride. It's all potassium chloride. If everything I have in my hand is exactly the same, whether it's all one element or whether it's all one compound, but it's all the same stuff, then that would be a pure substance. Pure meaning there's nothing else mixed into it. Yeah, I recognize for carbon dioxide or sodium chloride, let's use the salt example over and over again. For sodium chloride, I've got sodiums and I've got chlorines in my hand. But the sodiums and the chlorines are attached to one another in a relationship, and every sodium and every chlorine is attached to another sodium or chlorine in the same relationship, meaning that everything in my hand is a sodium-chlorine 1-to-1 compound. It's all the same stuff. That would be a pure substance. Another one would be a mixture. A mixture would mean that I've got my hands full of stuff, and you know what? There's a bunch of stuff mixed in there. There's some potassium and some potassium chloride and some sodium chloride and maybe a little bit of carbon. But whatever it is, not every structure in my hand is the same thing. Not everything is the same element, atoms of the same element, and not everything may be molecules of the same compound. There's other stuff mixed in. And so it's either a pure substance or it's a mixture. If you flip over on page 70 on figure 2.6, one of the things that we're going to talk about is the fact that mixtures can be separated based on the properties of their compounds. What he's showing here through these images, if you look top left, shows a mixture of sulfur and iron powder mixed together. And you can see pretty readily from that image that there's some stuff in there that's black and some stuff in there that's yellow. And you recognize, hey, they're together, but they're not the same. They're not in a molecule, because when they come together as a molecule, they would look the same. We see distinct things. So in our mind, this is a large enough mixture that we can say, hey, this isn't a pure substance. It's a mixture of 2 different things, the yellow sulfur and the black iron powder. Notice in the center on the top there, he takes a magnet and passes it through the mixture. And as the magnet goes through the mixture, one of the compounds of the 2 has a certain property that it's attracted. The metal, the iron powder, is magnetic and it's attracted to the magnet. The sulfur is not magnetic. It's not attracted to the magnet as it goes through. And so by passing the magnet through the mixture, we're able to separate out the iron from the sulfur. You can see here that if that white magnet were pulled away right now, a whole lot of the black stuff would be removed out. There'd be a higher concentration of yellow. And we can say by repeatedly passing the magnet through that mixture, and each time passing through, taking out more and more of the iron, that eventually, if I pass the magnet through and collect all of that and put it in one pile, and everything that doesn't get picked up stays in another pile, eventually, I would be able to virtually separate every single atom of iron and sulfur from one another. And it's because of the chemical properties of sulfur and iron that we're able to take a mixture and separate them out. Now, those properties could be a lot of different things. In this case, it's magnetism. In another case, we might have two different, let's say, liquids. And those two liquids have different boiling points. They have different evaporation points. And so when I take this mixture and I heat it up, I know that if I put the temperature above the boiling point of one, but below the boiling point of another, that I can evaporate all that stuff off. Right? So, think of it like a still. Okay? This is Kentucky, right? And though you guys don't participate, you understand moonshine. And so these stills, what they did was they would heat up this mash, heat up this mixture, and at different temperatures, certain things would evaporate off and boil off. And you would collect what boiled off, and you would get that, and you would concentrate it. And so if you're trying to boil off the alcohol, you would get the temperature to the point where that would boil off, and you could collect it, and it would be separated out from the mash and the mixture, all that other stuff, that nasty stuff that you don't want to think about where this stuff came from. So that's a chemical property of part of the mixture that we're using to separate out that part of the mixture. Now here's the interesting thing on this diagram. On the top we had sulfur and iron, and the magnet was able to pass through and separate out iron. And so like I said, eventually this mixture would turn into two piles of pure substance, one of pure iron, one of pure sulfur. And we use the properties of the components of the mixture to separate them out. Down below you see iron sulfide. Now iron sulfide is the same iron and the same sulfur as the top image, but we've added energy to it and we've made them react to one another. And the sulfur and the iron have formed a molecule of iron sulfide. The property of iron sulfide, it's a different thing than iron and sulfur. It's a third thing. It's a different thing than either one of the two. Kind of like the imagery of marriage, where you have a him and a her that come together to form a them, that are one, that are not based upon the properties of him or her, but is now a third thing, which is them. Okay? In this way, we have iron that has certain properties, and we have sulfur that has certain properties, and we can separate those things based on their properties. But when we react them together to form iron sulfide, it's now a third thing which has its own properties, which aren't just the properties of one or the other. It's not even the properties of the two of them mixed together. It's its own third thing. And when we try to pass the magnet through iron sulfide is not magnetic. And so because that third thing has been created, we cannot separate out the iron and the sulfur using physical means. This is a physical means. I'm physically separating things out. I mean, if we could just get on Miss Frizzle's school bus and get down to the atomic level or the molecular level, we could sit there and have these molecules go by us and go, okay, the atoms, okay, sulfur here, iron here, iron here, iron here, sulfur here, and separate them out. Physically, we could do that. But when we have iron sulfide formed, where atoms of the iron and atoms of sulfur have come together to form iron sulfide, a third thing which is not like any one of the components that make it up, we can no longer physically separate them. It has gone from being a mixture of iron and sulfur to a pure substance of iron sulfide, because everything in there is now iron sulfide. There's no iron, there's no sulfur, it's iron sulfide. Now the only way we can separate iron and sulfur at this point is to go through a chemical reaction. Physical is not going to do it. I can't get in there and separate the iron and the sulfur anymore because they've bonded together. The only way I can separate iron and sulfur at this point is to break those bonds. And breaking those bonds is not a physical thing, it is a chemical thing. It's a reaction. I have to reverse the reaction that brought them together. I have to separate them apart again. if I were able to take iron sulfide and break it apart into iron sulfur, then I could physically separate them again using a magnet, or using Miss Frizzle's school bus to get down at the atomic level and physically separate the different atoms. But when it's iron sulfide, I've got to go to some other method, and I've got to go to something chemical, not physical. So on top of page 71, it says the only way that we could get iron and sulfur out of iron sulfide is to decompose iron sulfide. Let's look at it real quick. If we take iron sulfide, we know that iron sulfide, we've got iron sulfide. Iron sulfide is going to break down into iron and sulfur, right? And we also know that iron and sulfur produce iron sulfide. So when I go from the different elements to form the molecule, now it's its third thing with its own unique properties, the only way I can separate these physically is to first of all separate them chemically and get them back to this form, and then I can physically separate iron and sulfur based upon the properties of iron and sulfur. And that's what this is talking about. So we've got mixtures, and pure substances. Now from the mixtures, we're going to have two different categories of mixtures. Hetero and homo. Heterogeneous and homogeneous mixtures. Real quickly, this will be for tomorrow because we're about to ring here, but what does hetero mean? Hetero? As opposed to homo?
Homo is the same.
Homo is the same, hetero is different. Okay? So when we have a mixture, we say that it's heterogeneous. It means we've got different things mixed together, and if we look inside of our sample at different places, we could find different things. The classic example, we'll repeat this tomorrow, of a heterogeneous mixture is Italian salad dressing. If you take the salad dressing and you let it set out, what happens? Things separate out, right? The oil's at the top, and things separate out based upon their density. When you have Italian salad dressing and you're about to pour it on your salad, what's the first thing you do? Hopefully, shake it up. Why? Because you're trying to take this heterogeneous mixture and make it as homogeneous as possible so that the first person doesn't get all oil. Now, if you have a homogeneous mixture, everywhere you look in the mixture, it's the same. It's the same throughout.